This is the outline of our talk. I'll start by presenting our project, introducing the background and the problem, and then I'll move over to describing our contribution, which is Arc, a programming language for stream and batch processing. And then I'll give some examples of how this language can be used. And then Max will talk about possible integrations with our work and Flink, and give some conclusions at the end. So in the big data landscape, or the data science landscape, Flink plays a really important role, because if you look around, there's a lot of frameworks, but they don't really support streaming computations. They're bound to batch data. So it would be nice if you could use some of Flink's functionality with these frameworks, such as like Pandas or TensorFlow. But there's a language barrier between these. So some of these are, or in the field of machine learning, most libraries are written in Python. Meanwhile, Flink runs on the JVM. So there's like a language barrier. And so to talk about what this means, if we consider that we have a pipeline where we use Flink together with Pandas and Flux. So Flux is a machine learning library in Julia. The first thing we would notice if we run a pipeline like this is that the frameworks, they're heavily optimized internally, but they don't really have any optimizations that are shared between them. So, for example, there's no resource sharing. So if there's multiple frameworks that need to use a GPU, there will be some contention, for example. And then the next thing is that there's some data movement costs, because each of these frameworks have internal data structures that might need to be materialized and written out as JSON, maybe stored to disk before they can be passed to the next framework. So what you end up is with a curve like this, where if you increase the number of frameworks you use, your performance will start degrading. But what you would really want is a curve like this, where the performance is independent of the number of frameworks. So a solution to this is to introduce a common intermediate representation, where you translate a subset of these frameworks into, and this representation can basically represent computations across the frameworks. And what this lets you do is you can combine them all into one function or computation, and then optimize it heavily. So this brings us to our contribution, and we can visualize or conceptualize the problem as an hourglass, where you have at the top frontends in high-level languages that implement like high-level programming models like streams, tables, and linear algebra. And then these need to be translated into low-level hardware instructions, or things that can run on like a Flink runtime. So in the middle here, these frontends go through an intermediate representation, which we have developed, named Arc, and then Arc generates these low-level instructions. So Arc is meant to run on a stream processor. Therefore, we have some abstractions that are relevant to stream processors. So for example, we support pipeline construction in the language as a first-class construct, also user-defined windows and out-of-order processing, and more things. And for optimization, we want to support both standard compiler optimizations, like partially evaluating expressions, but we also want to support dataflow optimizations, like taking multiple operators and fusing them into one, or splitting them into multiple operators, or reordering operators. So we want to support a lot of different optimizations. And our compilation pipeline looks like this. So at the top, we have the frontends, and they generate this ArcIR code. And the ArcIR code is compiled down into a dataflow graph, which is first logically optimized and then mapped onto a physical cluster. So, and for each node in this cluster, we compile it down into a jar file or a binary file. So for Flink, this might look like this. So you have at the top a Flink frontend where you, or a subset of a Flink frontend where you generate this ArcIR code, optimize it, and then you generate new Flink code that's optimized and runs hopefully faster. So to describe how this IR works, or what it is, it's a restrictive language for describing transformations over batch and streaming data. So in this language, the transformations are modeled by two kinds of types. The first are value types, which are read-only data types like vectors or unbounded streams or scalars. And then, then you have builder types, which are write-only data types. And the way this works is that you use the value types to write into the builder types continuously. And then when you've done your computation, you can materialize the builder to get the result. So you have a lazy computation built into the language. And for the dataflow graph, we look at how the values and builders depend on each other, and then we can build the dataflow graph. So if we move over to an example, we can consider this dataflow graph where we have a source, and we read from this source, map each value to the value plus 5, and then we split the even values and the odd values into different sinks. So the code will look like this. I won't go through everything, but the key thing is that we have these loops, 3 for loops. And the loops iterate over every element in the stream and then modify the element and write it into a sink. So for the mapper, we add plus 5. And for the filters, we conditionally write it into a sink if it's, for example, even or odd. So we have 3 loops in this picture. But this above graph could be optimized into a graph like this, where we have one operator that fused the 3 operators. So if we consider how we would do this in Arc, so on the left-hand side here, we have the unfused version from before. And on the right-hand side, we have the fused version where we've combined the bodies of the 3 loops into one loop. So we only have one loop now. And this basically represents one single operator instead of 3. And now Max will continue with the integration.
So I will talk about how Flink can benefit from an Arc integration. So first of all, Arc would be able to provide much more aggressive optimizations on top of the Flink pipeline. I will go into some examples after this slide. And then secondly, you would potentially be able to use other Arc-supported frontends if you want to use pandas or something like that, and you can use it together with the Flink frontend and have it optimized together. And then finally, the same way we rely on the compiler to fix our stupid mistakes in normal programming languages, we cannot rely on the data scientist to know the ins and outs of the data processing system they're using. So for example, maybe they're using a Scala collection on the JVM and it's quite inefficient, but they might not know it. So they should be able to write code they're used to, but it should be the compiler's job to actually optimize this and generate efficient code for it. So before I go into the next slide, I will talk about the black box problem. So in Flink, you would set up some transformations like this, and in Flink, all the user-defined functions are black boxes, so you don't really know what's happening inside. So you can't really optimize across functions in Flink. What you do currently in Flink is that you create an operator chain where you put them together after each other. But as we will see, there is a cost of having these inter-task calls. So we'll discuss some different types of fusion levels. So the first one is no fusion at all. And in this example, we have 4 mappers which are doing x plus 1. And this no fusion we can achieve in Flink by disabling the operator chaining. So each of these mappers will communicate across threads in Flink. And then we have the task fusion, which is what Flink is doing now. You would put them all in a chain in a single Flink task. And then this is where Flink currently stops. You can't do anything more than this. So then we can go further and have an invocation level fusion. So you would have a single function, but within that function you would have a for loop kind of imitating the chain. And then the strongest possible optimization is through partial evaluation, which is something you can do in Arc because everything is captured in the IR. But this is not something you can do in Flink. Yes, this is a quite trivial example, but it's just to showcase like the potential here. So this example is an experiment. It's similar to the previous example, but with 50 maps. And as you can see, the purple one is where we don't have any fusion at all. So it has the longest execution time. And then you can see that this is what Flink currently does, and then the invocation, and then the fastest possible is the instruction level optimization. So this is something you would want, although it's a quite like contrived example, but it showcases the point. And then I will just showcase some code we have right now, supported frontends. So we have a pandas frontend in Python, and then we also have a beam frontend in Python. So you can see up here the imports. So we import the frontends for pandas and beam. And then we can define some pandas computation, which is batch. And then we can actually use that in our beam pipeline. So it's actually used together with the pandas code, and this can be optimized across the libraries. But it's important to note here is that we don't actually run the pipeline here. We generate some Arc IR and some metadata about the sources and the sinks. And then, yes, this could potentially be Flink. It uses a very similar model to Beam. And one more thing. We are also working on a native Arc runner. We're building it in Rust for performance and memory safety. So yeah, one of the important goal is that we want to have like a common runtime where you can deploy all your Arc applications. And also because the JVM is a bit limited in using modern hardware, such as GPUs and remote direct memory access. This is also a reason why we choose Rust. And then some conclusions. In this talk, we have presented Arc and IR for batch and stream programming. In the future, we would like to support more frontends. Right now, it's just pandas and Beam. We are also looking into integrating state within the IR. And we also want to have like a common pipeline DSL, which means that it's much easier to implement new frontends. And if you're interested in Arc, you can come talk to us after. And otherwise, you can send us emails here. And yeah, that's it.
So thank you for the talk. First of all, I was wondering if you did some experiments with the Beam integration and if you saw some differences between having some implementation on a native Flink API versus something on the Beam API with and without your representation.
Yeah, I mean, we are not actually using the Beam runtime or anything like that. We're actually, the Beam frontend is just trying to imitate how you would actually write Beam code, and then that would translate into Arc. And then we haven't actually executed that on Flink or Beam. We have executed on our own native runner. I don't know if that answered the question, but yes, okay.
I have a question regarding this performance metrics you showed.
Yeah.
So you showed this graph where you had this with no optimization exactly. So do you have any intuition what causes this overhead?
Yeah, it's in the when you have a chain, because this is a chain of 50 maps. So for each function invocation, you would have to do a form of context switch where you have to load up the environment for the new operator. So if you do this 50 times, there will be an extra cost.
Okay, so just a function causes all this overhead?
Yes, I mean 50 in a row. So.
How much is this open at the state of the art? I mean, contributing to this, there is a GitHub repo.
Yeah, there is a...
Sorry, I missed it. Maybe.
That's no problem.
So yeah, down there there's a GitHub link to our organization.
And about the engine written in Rust, has it already started?
Yeah, it's we're working on it, so it's open source as well.
Okay, that's good. Always under the same organization.
Yeah. So okay. the Beam and Pandas example, we actually take that Arc IR and then we execute it in Rust currently.
Oh, that's great.
Yeah.
Okay, thank you.
The results that you presented with regards to the first two options, were they for Flink jobs or were they using your Rust-based runner?
No, this is purely Flink.
This is purely Flink.
It should have been more clear, sorry. Okay. Yeah, it's just Flink.
So here, essentially what we're seeing are different jobs that have the definition that you had in the previous slide, with separate tasks, separate threads, with the everything in a single task, and then the actual X plus 4 example.
Yeah.
Okay.
Yeah. So this experiment can also be found in the GitHub.
All right. Have you done something similar, but use exclusively Arc? So have you implemented in your runner some logic with Pandas and Beam, where Arc implicitly does this in compile, or is that something that you still want to target right now?
You mean if we actually compile it to...
Yes. Have you seen examples of Arc compile doing this exact level of optimization?
Yes, yeah, so we can perform both dataflow optimizations on the dataflow, or we can optimize the user-defined functions within the code.
Thank you.
Yeah.